My name is Ono. I'm working in the JTC Corporation. It's one of the largest EPC contractor. Especially, we are very strong for the liquefied natural gas. So today, I have a very big pleasure to introduce Alessandro coming from James Walker. Today he's specifically talk and teach about the soft seals for the hydrogen, and also the application is the valve sealing is the mainly. So we can learn a lot hydrogen and soft seal for the valves, right? So please.
Thank you. Okay, good afternoon everyone. Okay, we're ready? Okay. So, LNG, hydrogen, and CCUS. We would like to speak about these sectors, which are kind of different than the normal oil and gas sector for a lot of reasons that we will see, and how we can select the best material, best products to sealing those fluids. Just a very brief introduction about James Walker. We are a company that is present worldwide. We have 51 sites, commercial and production sites, and the production is in UK, Scotland, in India, in Belgium, and the commercial sites are basically in all over Europe and all over the world. We are very focused about the testing of our products, and that's why we want to speak about the most important oil and gas certification, which are API 6D, CSA, or the NORSOC, or the NACE. Everyone knows this kind of specification and the qualification processes needed to be qualified for this. That's one point to say, that these specifications are not always specific for hydrogen, for the hydrogen sector, or for the CCUS. And there's also kind of gray area sometimes on the cryogenic and LNG transportation and storage. Okay, just a few words about what is CCUS, carbon capture, utilization and storage. We know that in the last years, CO2 became an issue also for the environment, and the emissions of CO2 from the carbon-intensive industries, power generation, or the oil and gas industry that produce CO2. Which is a greenhouse gas. So the importance in the last year to capture and utilize CO2 and the storage to avoid the CO2 goes in the atmosphere became very important. This technology is not new, but in the last years it became very important also for the environment, and there's a lot of law that requires also the countries and the states to be in compliance of these laws. Okay, carbon dioxide is a gas in normal conditions. It is not just a waste product from the combustions, but it is also used in a lot of industry, like the beverages, and as chemical for the production, as a precursor to urea, or it also used as fire extinguisher, and it has a lot of uses. One of the most important things to say about CO2 and oil and gas and the sealing of CO2 is the supercritical state. Supercritical state of CO2 is present above 31 degrees and 74 bars. Supercritical CO2 is a very strong solvent. It is also used in the industry as a solvent, but it is also a challenge for a lot of materials that we can have in the valve industry, such as plastics, elastomers, and also compression packings for the content of PTFE in the graphite rings. In general terms, supercritical state is in between gas and liquid form. And one of the most important properties is the solubility of the substances that are in the supercritical state. And CO2 is one of the most challenging gas for these reasons. One of the things that we need to check before for the use of materials in the oil and gas and in general in the industry is the chemical compatibility of the materials that we use for the sealing. Elastomers in general are compatible from the chemical point of view, are compatible with carbon dioxide. However, the supercritical state of carbon dioxide can cause as well softening or cracking of the elastomers, but the most challenging part is the heavy rapid gas decompression damages that can occur with supercritical CO2. On a side note, supercritical CO2 can be also relevant to improve low temperature behavior on the elastomers because of the gas transition temperature shift. This is not the point here, but this is a consequence of the capability of CO2 in the supercritical state to enter in the elastomer chains. Saying that, we know that we have one of the most used certification in the oil and gas industry is the NORSOC M710, which consider just only 10% of CO2 in the fluid. The point is that if we consider the CCUS industry, we could have up to 100% of CO2 in the fluid. And this can totally change the behavior of the elastomers from the RGD point of view. We know that there's a lot of different compounds that can resist to RGD as per NORSOC M710 conditions, which are 100 degrees, 150 bars, and the fluid is 90% methane, 10% CO2, and there could be also some fluid with H2S. The point is that CO2 here is, we can have CO2 in much higher concentrations, and that is a real issue. If we look at these results, there's a lot of elastomers that we tested with 100% CO2, and in order to have the perfect results of 0,000, which is the best result you can have for the NORSOC M710, we had to lower the temperature of the gas. We also have some elastomers that actually pass the NORSOC M710 test with 100% CO2. This is a direct consequence of the capability of carbon dioxide in the supercritical state to enter in the elastomeric compound. Okay, the same problems with CO2, we can have the same problems, not for the RGD point of view, because RGD is not an issue for plastics material, but plastic, again, has elastomers are generally compatible with carbon dioxide. There's no chemical interaction between, for example, PTFE and carbon dioxide. There's no interaction with nylon or with polyethylene, but we are talking about, we want to focus on supercritical state of the carbon dioxide. And when it comes to supercritical CO2 with plastics, there's a lot of plastic materials that suffers from permeation of CO2 in the supercritical state, and that causes a certain material softening or a loss of mechanical characteristics. And another problem is that there's no qualification process or no certification. There's no standard for 100% CO2 in the supercritical state for the plastic material. We can test the valve with plastic seals in the valve, but there's no qualification process for the plastic materials. So we started to run testing on different plastic materials with this kind of configuration, which basically recreate the axial force that a plastic sit on a ball valve can be required to withstand. We stressed the plastic rings with 5% of deformation. Is it correct? 5%. 5%. And we put this plastic ring with this compression in a supercritical CO2 environment, and we actually discovered that PTFE, which is one of the most chemically stable plastic known to man, actually suffers from supercritical CO2, even if the liquid CO2 or the gaseous CO2 doesn't have this impact with the same plastic material. So again, the problem here is the supercritical state of carbon dioxide. And I want to stress this because supercritical state of carbon dioxide is very likely to be present in the carbon capture, utilization and storage industry, because it occurs just above 31 degrees and 70 bars. So when we have, for example, a facility where we storage carbon dioxide in a gas in a gas field, sorry. My English is not perfect as British, sorry. So we can actually have higher pressures, and also we can be above 30 degrees, because if we are in, I don't know, in the Middle East, ambient temperature could be very easily above 30 degrees, and we will have a lot high pressure to push the carbon dioxide in the ground for the storage. So it actually can occur, these conditions. And we discovered that other materials, this one is Devlon V, which is one of the our plastic materials that we use for the sit on the ball valves, has a perfect perfect resistance to CO2 even at supercritical state. So this is important. This is important to know before using these seals, and even so, it is important to test these materials before using. We have to know what are the capabilities of our materials before using in the valve. Another topic that I would like to introduce about supercritical CO2. It is also the graphite ring for a compression packing. compression packing, graphite is one of the most thermally stable and chemical resistant material that can be used, except for metals, of course. We all know the classical compression packing at the top of the stem of the valves. We all know what we are talking about. The problem is that to achieve fugitive emission performance, normally we need to use some kind of lubricants in the compression packing, the graphite, not just for the sealing itself, but it also needed to achieve low torque for the stem, for the valve. And the point is that supercritical CO2, as we see just before, it has a solvent action with PTFE. And basically the lubricants that are used in the compression packing industry have a high amount of PTFE in that lubricants. The problem is that if we are subjected to supercritical CO2, we can have this solvent action, and the PTFE can be removed from the compression packing, and this will cause two effects. We will start to have higher leakage because of the void that we will have in the compression packings because of the PTFE that is removed, and we will have a higher friction between the rings and the stem. It will start. We can have a raise of the temperature in that on the stem because of the friction. We will have higher wearing. So this is not what we want in this position, which is critical because the compression packing and the stem is the last barrier between the fluid in the valve and the environment. So we are talking about CO2. We know that CO2 is a pollutant, is a greenhouse gas. So we want a high level of resistance, of sealing. We want low level of leakages. And if we have lubricants with PTFE, and it's possible to have up to 5-10% of PTFE in the lubricants in the compression packings, that could be a real issue. On a side note, we are finishing the test with a new kind of lubricant in the compression packing rings, which have less than 0.1% of PTFE in the lubricant. So if we consider the whole packing, it's basically zero PTFE in the whole volume. That means that this friction and this loss of sealing capabilities is not present as in the compression packing with PTFE in the as lubricant. Okay. Besides CO2, we also have a new sector with hydrogen, because especially as fuel or energy carrier. Hydrogen in the oil and gas industry is present since a long time, so we know a lot about the chemical resistance of the materials to hydrogen. We know a lot about the stress cracking induced by hydrogen in the metals. It is quite studied, but again, there's no qualification process for the material and the sealing in the industry. Again, the NORSOC for RGD doesn't consider hydrogen. So we need to make some consideration also on it. Hydrogen sector, okay, there's a lot of utilization. We will focus more on fuel and energy carrier because it's where we need the sealing and we need the valves. We don't need the valves. Okay, We need valve also in the chemical plants. But we will focus as hydrogen, high concentration, up to 100% of hydrogen in the fuel, in the stream. There's a lot of different ways of hydrogen production. The colors mean how much, how can have, the impact of in terms of CO2 generated to produce hydrogen. There's a lot of different colors. Gray and black produces a lot of CO2. So these two topics also merge in this kind of sector. Okay, about hydrogen, we know is the most abundant element in nature. It is, as CO2 is a gas at standard condition. It's colorless, it's odorless, it's tasteless. So it is very difficult to detect a leakage without some device that can actually tell us if there's a leakage or not. The main problem is also the flammability range of hydrogen. It has a very high range, from very low concentration in air up to 74%. If you are working in hydrogen generation by electrolysis, we will have hydrogen and oxygen. And in oxygen, basically, hydrogen is always flammable, except for very high concentration or traces. So this is also another proof that we need to be sure that our materials will seal and will work with hydrogen. As for CO2, we can say that hydrogen, the compatibility of most elastomer with hydrogen is basically perfect. There's no chemical interaction, except for some kind of elastomer, but for the most used elastomer in the oil and gas industry, we have no chemical interaction whatsoever between the elastomer chains and hydrogen. There's a lot of study on this. We also run our testing with high pressure hydrogen, 100% hydrogen, high pressure, high temperature. And after 450-hour immersion, this is it does not have any meaning. It's just that we run the test and then we presented this work in other place. So we have data for 450 hours, but still it's 19 days. So it is more than enough to say that the chemical interaction and the loss of mechanical properties of the elastomer is basically zero. So this is another proof that hydrogen will not have any chemical or aging effect on the elastomers. The point is that during this test, and I underlined the minimum 100 bars, because we saw that we had to repressurize during the test, which means that somewhere this hydrogen somehow entered in the elastomer chains, in the elastomer compound. Hence, we need to also control and check the permeability of this gas in the elastomer. If we run the same, this same test with helium, the results will be more or less the same. No chemical interaction, no aging, etc. But we know that also helium is, elastomers are not permeable to helium. At least they are not permeable as hydrogen. Hydrogen, we saw that has high permeability in the elastomers and also in other materials. And this brings us to ask if hydrogen has also an effect on the physical, a physical effect on the elastomers, can cause swell or other. It actually doesn't cause swell, but the permeability is not zero. So we have actually hydrogen that permeate in the elastomeric compound. Again, we ran some tests. We also tested at different temperatures the best compound, and we saw that the permeation is quite low. So we are not worried. We know that the sealing itself is not an issue. The permeation is not that high to create a leakage. But this permeation can bring to RGD damages, because if we have an elastomer compound with a gas inside and we depressurize, the gas tend to grow up in volume, to expand, sorry, and that could cause actually damages, RGD damages. So we ran a test campaign on 100% hydrogen with the Norsok condition. So again, 100% hydrogen, 100 degrees, 150 bars. The pressurization rate is always around between 20 to 40 bars as per Norsok. We tested at 37.5 bars per minute. And we saw that basically we can't make the comparison between helium and hydrogen, even if the two molecules and the molecules of hydrogen is very similar in terms of hindrance and in terms of polarity, and in a lot of characteristics is very similar to helium. But helium doesn't cause RGD damages. We saw that actually hydrogen can actually cause RGD damages, and we can say that it's quite similar to the standard Norsok test, which has 10% of CO2 in the supercritical state. So that's an issue. And again, there's no qualification process, there's no certification that require 100% hydrogen test. If we run a test on a valve with hydrogen, we will have a perfect seal, even with a non-RGD resistance rubber, because there's no leakage. The point is that if this valve will face a rapid decompression, is it possible that if we choose the wrong material, which is not RGD resistant, is it possible that this seal will fail and we will have a massive leakage of hydrogen? And we already say that hydrogen is very dangerous in the atmosphere because of its flammability range. And it's very easy to find flames or sparkles in a field. So this one is one of the things that needs to be kept in mind when working with hydrogen and when we are choosing a material for the sealing. Same things we can say again for the plastic materials. We know from the literature, from history, from a lot of case study, that hydrogen is basically compatible with all kind of plastic material used in oil and gas. We are lucky there's no supercritical state for hydrogen. Okay, there is, but it's not easy to achieve the supercritical state of hydrogen. So basically it's not an issue in the industry. But of course we need to check the permeability. Again, it's not is not helium, it's not the same. Even if they are very similar, the permeability is not the same. So if we have a high permeability permeation, we can have a leakage. If we choose, I don't know, the wrong seat material or the wrong lip seal, we can have a leakage. And again, we are talking about hydrogen, which I know I'm stressing it, but is very dangerous to have. So it's very important to test and know what we are asking when we are talking about sealing of a valve and sealing materials. Of course, after that, we also have the graphite, the compression packings. Again, there's no chemical interaction. There's no swelling or softening whatsoever with hydrogen. The media compatibility of graphite is basically infinite. There's very few chemicals that can interact chemically with hydrogen, with graphite. The temperature range is also very interesting for the hydrogen industry because it can also work with liquid hydrogen. So again, how can be sure that the graphite rings or the gaskets, the graphite gaskets, can work with high level of, with low level of leakage? I'm talking about fugitive emissions performances. One of the example that we made is that we have some products that can achieve a level of leakage that can the leakage is like the equivalent of a golf ball of gas per year. They are British, they don't use metric system. Golf ball, it's okay. The equivalent volume of the golf ball. So it is very low, but are we sure that these kind of levels, performance, can be achieved also with hydrogen? Because most of the ISO 15848, which is one of the most important specification in the valve industry for the compression packing, and I believe also for the chevron packs, but I'm not sure, but for sure for compression packings on the stem, for the control valve or the ball valve with a quarter turn movement. This is the most important specification. It is usually the tests are run with helium or methane, and it is possible to achieve the highest class, which is AH, in particular condition with the right design, with the right material and the right compression and the fitting. We discovered that at least for the non-static position, such as the valve stem, hydrogen does not behave at the same level of helium. So it's not enough to test the valve with helium. We can achieve fugitive emission performances with this kind of product. We had to change the design of the product. This is not the regular, let's say, the regular compression packing. We had to put some dense graphite ring with high density to improve the resistance to permeation of hydrogen to achieve class BH with ISO 15848-1. It is class BH. It is a great result. We had to change the design to achieve these particular performances. So again, when it comes to hydrogen, it is important to know what we are facing. It's not helium. The permeation rate, the the movement of the hydrogen in the materials, it appears to not be the same. And speaking of graphite and graphite seals, EN 13555 is one of the most important certification for the gaskets, for the flat gaskets and the graphite gaskets in the pipelines or in a flange connection. Usually this test is run with helium. It can be done also with methane, but helium is of course more challenging. It is run at ambient temperature, 23 degrees, with 40 bars. And it recreates the condition of compression and relaxation on a gasket in a flange connection. This is the flat gasket, the flange connection. And we recreate the same test using 100% hydrogen with the same temperature and same pressure. We discovered in differently than the compression packing, which is a dynamic sealing. This one is basically a static sealing. Of course, there's the compression and relaxation between the valves, but there's no movement. So this is a static flange, a static seal. And we discovered that actually we can make a good comparison between helium and hydrogen in these kind of conditions with static condition. And if we create the graph based on the 13555, this graph is basically very similar, and it's basically the same as the same test with helium, with the same condition, pressure and temperature. So there's something with the mobility of hydrogen that need to be tested and need to be checked, because the sealing test on a valve could be not enough. We need to test the materials in another way, and not just with a pressurization test on a valve. Some of those things can be also said with LNG. Natural gas is basically methane with traces of other gases. It's again colorless, odorless, is non-corrosive, is non-toxic, and so again it could be difficult to detect a leakage here. So again, it is important to achieve high level of sealing. Boiling point is minus 162, which is important because one of the most effective method of transporting and storage of of methane is liquid natural gas. We need to the volume, the equivalent volume of the liquid instead of gas is 1 to 600. So having liquid methane has great advantages when it comes to transportation and storage. It's also good because it's using as fuel, like in the last years. It is good because we can reduce the emission of CO2, nitrogen oxides, and sulfur oxides. Again, we need in this kind of sector, of course, elastomers are ruled out. They can't work at minus 162. So it leaves us just with plastic material and graphite. Again, the first thing to control is the compatibility, the chemical compatibility between graphite and methane. There's plenty of study, there's a lot of history in the oil and gas sector that can that allow us to say that there's no chemical interaction between graphites and methane. Again, the temperature range of graphites is very, very wide, so it can be applied without any problem to the LNG sector. Again, we can use the 15848 certification, but in this case, the normal 15848 could be enough, because one of the temperature classes goes down to minus 196, which cover the LNG sector. We tested and we have a lot of case studies with the cryogenic conditions, and in this kind of sector, also the design of the valve and the material used in the valve are very important. It's not enough to test the material. We need to test the valve. That's why 15848 is very important in this sector. Again, we need to test also the flange connection. The graphite here, again, is completely compatible material, but EN 13555 doesn't require low temperatures. We don't have a specific test for the cryogenic sector for the flange connection. So again, we recreate the same test using helium as the test, but we change the temperature at 40 bars, which is much higher than the storage and transportation LNG. But we tested it, and we developed this. Again, we had to change the design of the graphite gasket to face the relaxation and the stress, the compression stress caused by thermal expansion and thermal retraction, and not just the compression of the flange and the gasket between the flange. So we tested it, and again, is another test that is not a standard. So again, we need to be sure that when we ask for something that is qualified, it doesn't mean that it is qualified for the purpose that we need. So as I was saying, we used the 15848-1 test because one of the temperature classes goes down to minus 196. We tested on a valve because 15848 is a test on a valve. It's not a test for the compression packing itself. We also checked the temperature, that it was the actual temperature on the stem in that position. It was minus 139 degrees. So we are in the cryogenic state. It was also, yeah, there was no extension. So the temperature was that low because of that. Usually in the in the cryogenic sector, sometimes we have long extension stem, and the compression packing doesn't see that temperature. It works at higher temperatures, so it's easier to achieve fugitive emission performances. Again, we could achieve class BH, but again we had to change slightly the design. We put a carbon graphite ring, dense carbon graphite ring, to as a shield for the low temperature and the environment. Okay, the other material that we can use for the sealing in the cryogenic test sector, of course, is the plastic material. We know that PTFE can go down to minus 196. Usually is not used the classic PTFE, but the modified PTFE, which has better performance at low temperature. The chemical interaction and the physical interaction is basically zero between PTFE and methane. We know that. There's plenty of examples in the literature. We have a lot of case study. This is methane is used since very long time. So there's a lot of examples that says that allows us to say that PTFE is completely compatible with methane. And the point is, again, that there is no certification whatsoever for the lip seals or the plastic sealing in a valve. It does exist the BS 6364, which is a specification for the valve in the cryogenic sector, for the cryogenic service. But it's not a test that requires some performance from the seal. It doesn't require anything from the seal. It requires, of course, that the valve should not leak, so the seal should work. But there's no test on the seal itself. So in Scotland, we have our Center of Excellence for the thermoplastics. Mr. Andrew Hambleton here can agree with me, which is a Center of Excellence. And we have a test facility that can allow us to recreate some pattern of temperature and pressure that can occur in the cryogenic sector when we have, for example, in a LNG tank, we have a certain pressure for a long time, minus 162, because we have liquid methane there. But of course, is sometime we need to fill or to refill the tank or to empty the tank to move the fuel. So the conditions at that the seals will face will change. We could have low pressure. We can go from minus 162 to ambient temperature, and then we can go down again to minus 162. So we need to be sure that our seals and our material that we choose can actually go back to cryogenic conditions after the heating, and that they can achieve the same level of sealing. So this test is basically recreates this kind of condition. We pressurize the device, then we go down to minus 196. We go up to ambient condition, to ambient temperature. Sorry. We go up to 140 degrees in this case, but we can also choose different temperature, of course. Then we go down again to ambient temperature, and then we go down again to cryogenic conditions. And during all this pattern, we can control that our leakage, the leakage that we detect, is hopefully zero, or at least much below the general maximum allowable leakage given from the various certifications or the various qualification processes. This one is, I believe, was class 300. We tested up to class 1500, and all the results was kind of good. Again, I'm stressing it, I know, but it is not a standard test. We don't have a qualification test as for O-rings in the oil and gas sector. We can have ISO 23936 and the NORSOC and qualify perfectly the O-ring and the elastomer. We can do that with compression packings or with lip seals or valve seat, plastic valve seat. So in conclusion, oil and gas standards are important, of course, but are not always enough to predict the suitability of a sealing material, especially when it comes to these sectors. The hydrogen sector, we can have high temperature, high pressure, 100% hydrogen. Helium testing is not always 100% comparable to hydrogen. We can't be sure that helium test gives the same results of hydrogen. We saw it for the RGD, for example. We saw it also for the compression packings with the dynamic conditions. For the CO2, there's no qualification process at the moment whatsoever for CO2, which is not a problem, an issue, if we are talking about gaseous CO2 or liquid CO2. But if we have supercritical CO2, this lack of testing and certification could be catastrophic because of all the evidences that we already see. Plasticizing of elastomers, deformation of plastics, PTFE removal from the compression packing. So it can bring to a lot of problems. And for LNG, the cryogenic qualification are not always clear. 15848 does comprehend cryogenic condition, minus 196, but not all the other most used qualifications. So for that work, I would like to thank Andrew Ambleton here and Jakub Marsik, which are our director and manager for the graphite materials and plastic materials. And I also would like to thank Andrew Douglas, which is our manager for the elastomeric materials, and I took a lot from his work from this presentation. Thanks so much. I'm sorry for my English. Yeah.
Alessandro, thank you very much for the impressive presentation. Personally, I'm mostly interested in the James Walker is doing a lot of the higher level testing to the standards to know the exact the necessity of the technology, right?
Yeah. Okay. As I was trying to say is that James Walker is trying to run a campaign of testing because we discovered that actually there are issues with these fluids that were not investigated in past. We know that methane, hydrogen, and CO2 are very known gas in the industry. There's a lot of history, but now, especially with higher pressures for hydrogen, and from my side, since I come from the rubber industry, the supercritical CO2 for elastomer could be very, very dangerous. And the normal specification as NORSOC M710 is not enough. The 10% of CO2 is a challenge, and the test itself is okay for the most of the oil industry. When it comes to crude oil or the normal gas fluids, there's also the total test which comprehend 20% of CO2, and that's fine because usually we don't have that high level of CO2 in these streams. But when it comes to the carbon capture sector, we are facing 80, 90, 100% of CO2 at high pressures, because if we want to inject the CO2 in the soil, in the ground, to capture and avoid the CO2 go in the atmosphere, we need high pressures. But supercritical CO2 can, carbon dioxide can reach supercritical state or even at 30 degrees. So if we are, I don't know, we all know Aramco. Aramco is Saudi Arabia. And basically they have more than 30 degrees all the year, maybe even in January. So it is a real challenge. So that's why we try to focus on this on these issues, and we are doing a lot of tests. Our luck is that in Scotland and for the compression packing and also for the elastomers, we can make our own test that can be witnessed. And the most important is that we can arrange the test with the customer, so we can test the valve, because especially for compression packings and the plastic seals, also the design of the valve is critical for the achievement of the material. When an O-ring is basically doesn't require a specific design, a lot of times, especially for critical conditions, high pressures or high hydrogen, we also need to have the design of the housing of the seal that is fit for the purpose, not just the seal. So that's why this capability of the testing could be important to recreate the various problems that we can have in the industry.
Okay, thank you very much.
Thank you. Is there any other question? Thank you, because my English is enough. Thank you for listening. Thank you.